Okay, now we're going to move on to combining uncertainties. So that is, if you are, as we usually are with experiments, getting your results to combine together through a calculation or even just addition or subtraction, you need to have a way of working out what the overall uncertainty at the end is going to be. So let's take, for example, stacking two objects on top of each other and working out what the height of those objects will be. Now, if I measure length A to be about 2.4 and length B to be about 1.4 centimetres, obviously we're using a ruler here that has a precision of 0.1 centimetres, 1 millimetre. Then by combining the two together, I will get an overall length of 3.8 centimetres. But what is that combined error going to be? What is my absolute uncertainty for my length going to be? Well, to do this, let's think about it this way. The biggest possible length that I could have would be 2.4 plus my 0.1 centimetres, so 2.5 centimetres, plus my 1.4 plus 0.1 centimetres, so plus 1.5 centimetres, which gives me an overall length of 4 centimetres. My smallest possible length, if I take the smallest versions, would be 3.6 centimetres in total. So this means that I have my actual overall length, 3.8 centimetres, with a maximum possible length of 4 centimetres, that's 0.2 centimetres greater, and a smallest possible length of 3.6 centimetres or 0.2 centimetres less. So my absolute uncertainty when adding A to B is my original measured length, 3.8, plus or minus 0.2 centimetres. Or basically, the quicker way to think about it is, when you add two values, you add their absolute uncertainties. So you take your calculated value, in this case A plus B, put your plus or minus sign, and then your absolute uncertainty in A plus your absolute uncertainty in B. What about when we subtract two measurements? Well, let's think about measuring the extension of a spring. Here I have a spring that doesn't have a mass on it. And here I have a spring that's been extended once I've added a mass. Now if I look at my ruler, my original length of 3.7, again plus or minus 0.1 absolute uncertainty in the ruler. My extended length is 5.9 plus or minus 0.1 centimetres. But again, once we've calculated the extension of 2.2 centimetres, we need to think about the absolute uncertainty for the extension. Now, the biggest extension, if I take the plus 0.1 option on the longer reading, and the minus 0.1 on the shorter reading, gives me 2.4 centimetres. The smallest extension, if I take the minus 0.1 on the longer reading and the plus 0.1 on the shorter, gives me 2 centimetres. So again, I find myself in the position where I've got my calculated extension, 2.2, plus or minus 0.2 centimetres. And that's plus or minus the absolute uncertainty in our original length and our absolute uncertainty in our mass added together. So just like with adding two measurements, if I subtract two values, you add their absolute uncertainties. But what about when we multiply them together? Well, this might seem a little bit counterintuitive, and you don't need to know the maths of y. You can go and find out, but you do not need to know. All you need to know is that when you multiply two values together, you add their percentage uncertainties. So, similar to what we did with adding two or subtracting two values, but this time we're looking at the percentage uncertainties, not the absolute uncertainties. So, let's imagine a light bulb, and running through that light bulb, we are measuring a voltage across it in parallel and a current running through it in series. So we have a voltage at 5.9 plus or minus 0.1 volts and our current of 0.12 plus or minus 0.01 amps are absolute individual uncertainties. Now, power is current times potential difference times voltage. And so if we multiply those two together, we can get a value for our power of 0.7 watts. But we now need to know what the uncertainty in that is. And as I said before, to get the uncertainty when you're multiplying, you take the percentage uncertainty and add it to the percentage uncertainty of your other value. So the percentage uncertainty in our current was 8.33%. In our voltage, it was 1.69%. Add them together, and I get an overall uncertainty in my power of 10.02%. So that's what my uncertainty in the power is as a percentage. You might well then be asked to convert it back into an absolute uncertainty. How do we do that? Well, we know that our power is 0.7 watts from our calculation. We also know that it has an uncertainty of 10.02%. All we have to do is find what 10.02% of 0.7 is. And to do that, we take our 0.7, we divide it by 100 to get what 1% is, and then we times it by the combined percentage uncertainty to give us 0.07 as our absolute uncertainty. And then we just switch that back into its traditional form. But you will notice here that while my absolute uncertainty was 0.07 watts, I've rounded it up to 0.1 because my reading was only accurate to 1 decimal place. It's always worth showing you're working when you do this though, because you can never be entirely certain which way the examiner is going to go on decimal places and sig figs. Always show you're working. Now when we divide two measurements, we do exactly the same thing. You add their percentage uncertainties. And again, you don't need to know why you do this, although if you do want to know why, I will put a proof up on the website. But a classic example for this is looking at resistance. Now, again, we can use our trusty voltmeter and ammeter combo. If we wanted to work out what the resistance of a resistor was, we'd use the equation resistance is voltage divided by current. I stick my numbers in and I get a resistance of 49.2 ohms. And notice how, despite the fact that our current is to 2 decimal places, because our voltage is only to 1, I've rounded it up to 1 decimal place. Now, as we saw before, the percentage uncertainty in the current was 8.33% and 1.69% in the voltage. And just like before, we can add them together to get a combined percentage uncertainty of 10.02%. But now we apply that to our result that we got for our resistance. And again, we just have to find what 10.2% our total uncertainty for the resistance of 49.2 ohms is. So again, we divide 49.2 by 100, multiply it by 10.02% to give us 4.9 ohms. And then we stick that back into the absolute uncertainty form. 4.92, my calculated value, plus or minus my absolute uncertainty obtained from using the percentage and finding out what that percentage is of my value. Finally, if we look at raising to a power, if you imagine that you are trying to work out the volume of a cube, and this cube here has got sides of length, let's say 1.3 centimeters long. Now the absolute uncertainty in the length is 1.3 plus or minus the precision of my ruler, 0.1 centimeters. The percentage uncertainty in L therefore is my absolute uncertainty divided by my reading multiplied by 100 to give me 7.69%. Now, when we're finding the volume, we are doing our length times length times length, length cubed. And so working out my volume, I can calculate it to be 2.2 centimetres, keeping it to the same number of decimal places. But if L cubed is just L times L times L, then I effectively have a reading with an absolute uncertainty multiplied by a reading with an absolute uncertainty multiplied by a reading with an absolute uncertainty. And so basically, just as we did beforehand when we looked at multiplying values, we add their percentage uncertainties. So here I effectively have 3 lots of L, so I need to add their percentage uncertainties to each other 3 times. And adding those together is the same as doing 3 times it. So if I take my percentage uncertainty in L, times it by 3, that gives me my overall percentage uncertainty in the volume of the dice. So basically what that boils down to is when you raise a value to a power, you multiply the percentage uncertainty in that value by the power. And it might be worth noting in this situation that we ignore constants. So let's say I have a circle here and it has radius of 5 plus or minus 0.1 centimetres. Of course, the equation for radius of a circle is pi r squared. Now I have an r to a power here, so I have an absolute uncertainty. I effectively have r times r, so I'd need to convert that into a percentage uncertainty of 2%. I then work out what my area is. Pi times 5 squared gives me 78.5 centimetres. I ignore, for the purposes of uncertainty calculation, my pi here. It's just a constant. It has no inherent uncertainty, so I don't need to worry about it. Now, to work out my total uncertainty for the area, I just take the uncertainty that I had in r, and because it is squared to the power of 2, I times that uncertainty by 2 to give me an overall percentage uncertainty in my area of 4%. I hope that's been helpful. If you came to this video from the website, then please now go back and have a go at the practice questions. And space engineers, if you get stuck, please do email me.